Let us today address that issue that we left unaddressed in the previous video, namely showing that this topology tau on X really is a topology which we defined in terms of a basis B on X. So we start like this: let X be a set and B be a basis for the topology tau on X, and I have kept topology within quotes because we have to show that it's really a topology. And let us recall what the definition of tau was. So let U be any subset of X, then U will belong to tau if and only if this condition is true. If X is an element, or I should say point, if X is a point in U, then there exists a basis element N in B which contains X as a point and which is itself contained in U as a subset. Such sets U are elements of tau. Let us now prove that tau is a topology on X. The following is vacuously true. So we now first of all want to check whether the empty set is an element of tau. So we apply this exact condition with empty set in place of U. If let us note carefully this statement: if X belongs to the empty set, then there exists the basis element N which contains X and is itself contained in the empty set. This is an if-then statement or an implication whose hypothesis this is false. So the implication is vacuously true, but true nevertheless. So that is why the empty set really is in tau. Next, let us show similarly that the set X itself is also in tau. To show that X is in tau, we start like this. Now we have X in place of U and say X is any point in X. Now you recall the first condition in the definition of a basis for a topology. Any element in the set or any point in the set is contained in some basis element N. Do you remember what I said in the previous video? That the basis element, when taken together, they cover the entire set X, in the sense that their union is equal to X. So obviously, no matter what point from X you choose, that will belong to some basis element. And clearly N is a subset of X. Why? Because originally B is a collection of subsets of X. That's why any element from B you choose, that is after all a subset of X. So these conditions are true for X if you take X in place of U, and that is why X also belongs to tau. So we have ended up verifying the first condition in the definition of a topology for our tau, that tau contains both the empty set as well as the set X. Next we go for arbitrary union of any subcollection of tau. In order to consider arbitrary union of elements of tau, we have this indexed family of elements of tau, which is whose members are these U alphas, and the index set is J, which simply put is this, that for each label alpha coming from J, U alpha is an element in tau. So basically U alpha is a subset of X, and let U be their union. Our aim now is to prove that U also belongs to tau. So we take any point X in U, then X obviously belongs to some U alpha. X belongs to U alpha for some label alpha, because U is their union. Now each such U alpha belongs to tau, so this particular U alpha also belongs to tau. So the condition that we have on the elements of tau would be true for this U alpha. That means for this point X in U alpha, there exists a basis element N in B which will contain X and will itself be contained in U alpha as a subset. But each U alpha is contained in U because U is their union, so that way this N is also contained in U. So we have ended up finding a basis element N which contains X and which is itself contained in U. So that is why U is an element of tau. Next we go for finite intersection. For finite intersection, we are not straight away going to the general case where we have any finite number of sets involved. Let us first consider the case where we have only two sets, U1 and U2 in tau. Our aim now is to prove that U1 intersection U2 is also in tau. So we take any element X in U1 intersection U2. Then X is in both U1 and U2, and because they are elements of tau, so we are going to have this next, that there will exist for this point X being in U1. For that fact, you will have a basis element N1 which will contain X and will itself be contained in U1. Similarly, because X also belongs to U2 and U2 is also in tau, you will have another basis element N2 which will also contain X and will itself be contained in U2. Now X is in both N1 and N2, so X belongs to their intersection, and because N1 is a subset of U1 and N2 is a subset of U2, so N1 intersection N2 is a subset of U1 intersection U2, simple set theory result. But now you recall the second condition in the definition of the basis B, that whenever you have a point in the intersection of two basis elements, then there exists a third basis element N3 which contains that point and is itself contained in that intersection. Hence, we have a basis element N3 such that N3 contains X, where is that? Here, and N3 is a subset of U1 intersection U2. How are we concluding this? Using this containment and this containment. N3 is contained in N1 intersection N2, which itself is contained in U1 intersection U2. So this way, we see that any point chosen from this intersection is inside a basis element, and that basis element is entirely contained in this set. So our condition now is true for U1 intersection U2, and as such it belongs to tau. But now what do we do for the general case where we have any finite number of sets involved? Simply we apply induction. The induction argument is absolutely straightforward, but let's go through the details. So now we have any finite number of elements in tau, and our claim is that their intersection is in tau. And for this we are going to apply induction on the number of sets involved in this list. And the case where there are two sets has already been handled. And let the claim be true for some integer n greater than or equal to 2. So this is the base case and this is our induction hypothesis. Now for the induction step, we take n plus 1 elements in this list in tau, and let us give them some other names v1, v2 up to vn plus 1. Now by the induction hypothesis, we immediately have the fact that the intersection of the first n of them is in tau, and by what we proved earlier means this case. See, this is in tau and this is also in tau, so their intersection will be in tau, but that is actually the intersection of all these elements in tau. So that way we have the induction completed here and we have our claim proved. So now we can say that yes, the way we define that tau, it really is a topology on X. And after this, there are other things I already said in the previous video. The next thing that we will prove is that any open set, that means any element in tau, is the union of some basis elements. And then there are other results also. That we will, however, do next week. So see you next week with these things. Until then, this is me, Lucifer from a mathematical room. Have a nice day.